Thank you, Sally, for the invitation, and Suni for organizing. And also, thank you all for coming here. I did not realize I was kicking off the series for the quarter. So I'm actually very, very excited about that. Having come just from the University of Illinois, I think I'm still a little bit used to the semester system. So if I, by mistake, say semester instead of quarter, please forgive me. So as Sally had mentioned, I am new here, relatively new. I actually did my PhD at Stanford, so I'm kind of in a way coming back. I was a graduate student here about 10 years ago, a postdoc, and then I worked at Intel Corporation in industry for a while before taking on this job at University of Illinois Urbana-Champaign. And so it's kind of a homecoming for me, and it's really a privilege to be here today. I should mention that I'm in the electrical engineering department, and that my group has a website called poplab.stanford.edu. So if there are any technical points that you miss, any papers you'd like to download, more information you'd like to pick up about myself or my students, please look over there for additional details, or of course contact myself or any of my students as well. So I'd like to sort of begin by telling you what motivates us. So we're electrical engineers, but we're also physicists. We're material scientists. We're also mechanical engineers in my group. And the way we tend to look at things is we tend to look at electronics from the point of view of energy and power, right? And I came across this just a few years ago. You probably have heard of the IBM Watson, who was the Jeopardy champion, beat these two human beings. It was big in the news. What the press releases didn't usually tell us is that the humans were competing with 20 watts of power, and IBM Watson was competing with 200 kilowatts of power. So that's about a factor of 10,000 in terms of that's how much the game was stacked towards the machine compared to the humans. As an electrical engineer, I'm also trained to always think about Moore's law. And of course, I'm sure you've heard of Moore's law. Basically, every 2 years or so, things are scaling down smaller and faster and so on. But as of today, we've reached 25, 35 nanometer dimensions in current commercial processors. So clearly, we can probably get another factor of 10 in terms of just traditional Moore's law scaling, in terms of size, speed, and probably even power dissipation, right? So the question is, how do you get from maybe a factor of 10 to factors like 10,000 or maybe even 1,000 in terms of things that we're trying to do? Another thing which I found online, there's lots of things you can find online, as I'm sure you know. Another thing I found online was this picture, which is a picture of an egg cooking on a computer processor. This was actually done circa 2005. I don't even know if this website's still active. In 2005, the Pentium 4 was consuming over 100 watts per square centimeter, or putting out that much heat, essentially. And if you've ever unscrewed a light bulb immediately after turning it off, you know how hot 100 watts will feel on the surface of a light bulb. Of course, imagine putting that in the size of the postage stamp, right, which is the size of one of these computer processors. And you can imagine why the egg was cooked pretty quickly over there. So since 2005, all the major electronics manufacturers have been limited by power and heat dissipation, right? So that's been sort of a problem. I actually started a course on the fundamentals of energy and electronics at the University of Illinois, which I will be teaching here, adapting it for Stanford for the quarter system and so on, probably next year in 2014. So little plug for the course. I forgot to mention actually earlier, the processor that was underneath the egg over here was an AMD processor. And when I was working at Intel, we used to joke about that. Of course, a few years later, one of my graduate students, David Estrada, actually repeated the experiment in one of our outreach activities using an Intel processor. So clearly, you can do this both with AMD and Intel processors. You can make breakfast. OK, that's not what they were made for, but that is an interesting side effect. So Moore's law has been good for many things, obviously, as I'm sure you know. But from an energy point of view, Moore's law has been very, very good from the point of view of individual transistors. Transistors are the individual switching components inside the silicon chips. So from the point of view of individual transistors, we've actually been scaling down the energy consumption exponentially as we've been scaling down the dimensions, such as right now, we're probably here somewhere, we're at less than 1 femtojoule per individual transistor switch. The reason that we're still able to cook the egg is because each CPU has on the order of 1 billion transistors. And not even all of them are switching. Some of them are sleeping, but as they're sleeping, quantum mechanics essentially makes them leak current, right? So that leakage current itself accounts for something like 50% of the power dissipated in CPUs, maybe a little bit less if they're really well designed. If you look at the fundamental limits, if you talk to physicists and look at fundamental limits for energy switching per transistor should be on the order of kB times T, where kB is the Boltzmann constant. So we're still something like a factor of 1,000 to 10,000 today versus what some might call the fundamental switching limits of energy per switch. If you look at a complete opposite end of power consumption, this is the US data center power use. So this is only in the United States alone. For the last decade or so, every 5 years, the power consumed by data centers, basically by the computing cloud, by our Google searches, by our Amazon accounts, by our bank accounts, and so on. Anyway, that power has been doubling about every 5 years. You might even say there's a Moore's law even in there, right? And I don't think this is going to slow down any time. So right now, we're at about 10 gigawatts of power used for data centers in the US, of which half is used for cooling them, for air conditioning the data centers, right? About half. Newer data centers that are being installed right now are more energy efficient. However, on average, the estimates done by Jonathan Koomey here at Stanford show that about half the energy used is used for cooling for the already installed data centers. So I tend to work with femtojoules and nanowatts and really small power units. So when I first saw these large numbers like gigawatts, I said, I need to look this up. What exactly is a gigawatt in terms of what can I relate to? It turns out one large nuclear power plant puts out about 1 gigawatt, and an entire country like Argentina uses 12 gigawatts. So the data center usage in the US is the same as the country of Argentina, all electricity in Argentina, not just their data centers, all the electricity in Argentina. Worldwide, there are some estimates that actually show that if you look at cloud computing or data centers overall in the world, if cloud computing were a country, it would be the 5th more energy consuming country in the world, right between Japan and India. Some other estimates think it's about something like 12th. So it depends on which study you read. Regardless, whether it's 5th or 12th or some number in between, whether it's Italy or Spain or India, the point is these are very, very large numbers. So there's a lot of energy being used by computing. This is what electrical engineers have traditionally done, right? Computing. And of course, also the expected growth, as you saw earlier, is not expected to slow down. This is still projected to be about 12% per year in terms of new data centers being installed. There's also electronics power issues in space, it turns out. And space, talk about a really extreme environment, right? There's no way to kind of go in there and change the battery or fix a leak too easily. This was a very, very unprecedented leak fixing mission, a spacewalk actually done by NASA space station astronauts, who essentially the cooling for the electronics on the space station, the cooling for the solar rays actually sprung a leak. So the ammonia was leaking out into the vacuum of space. So these guys actually had to go out there and fix that leak. So you can imagine for military or purely scientific applications, satellites and so on, the Mars rover and so on, these actually can be pretty important issues as well, even though maybe the power used here is not so large. But if you have remote electronics, this is a big deal. A little bit closer to home, this is some numbers from my old house in Champaign, Illinois. I checked this with one of these kilowatt type meters, electricity meters. I guess no surprise, my refrigerator, 150 watts, time average, was the biggest electricity hog in the house on average. But my big surprise was to find out that my digital video recorder, supplied by Comcast, I guess, was consuming 50 watts day and night. And it was on day and night because it needs to be on so that it records, the TV shows that I'm missing when I'm not home, or the soccer games that I'm trying to record for the Premier League and so on. So that's kind of an interesting discovery. Then I realized that there's about 50 million of these high-definition DVRs in the US, if you go by numbers published. So about 2.5 gigawatts of energy use, of power use, is only due to these digital video recorders that you and I own. I was told that some of the newer DVRs are a little bit more energy efficient. I tested the one I have here at Stanford, and I think it was something like 20 or 30 watts. So the numbers remain comparable. Google searches. One Google search equals 1 kilojoule, according to this Google blog spot published a few years ago. There's about 100,000 searches per second that we are doing in Google. And so the Google search part by itself, not the Gmail, not the other things that Google does in terms of storing files, that's about a significant fraction of a gigawatt itself, right? To compare that with other energy I guess, units or examples that we're familiar with, your car hurling down the freeway consumes 1 kilojoule in 0.01 seconds, so that's pretty quick. Your body just sitting down consumes or generates that heat in about 10 seconds, and my laptop sitting over there needs 1 kilojoule to function for 1 minute. Next time you do a Google search, think about that's the energy required to power your laptop for 1 minute when you just did that Google search. And I believe that's not the energy required to transmit the signal, bounce it off all the networks and so on. This is just the energy, the power bill basically that Google gets, right? So there's actually a lot more energy. So this is probably an underestimate of Google search related energies. So what does my group do? My group does not necessarily work on data centers. We work more on the nanoscale side of things, the nanomaterials side of things. But I'd like to think of what we do as working on two sides of the same coin. One of them is looking at lowering power at its source, working on nanoscale devices, sensors, and circuits. Remember, everything starts from the nanoscale in terms of transistors, interconnects, memory, and so on. So that's going to be the first part of the remainder of my talk, and then I'm going to talk a little bit about how some ideas we have in terms of harvesting and managing the heat that inevitably electronics will be creating. Of course, we're academics, so we're always seeking a fundamental understanding of things, but we're also engineers, so we'd like to link things back to practical applications. So again, I'm not a material scientist, but I work with materials, and I think nanomaterials were part of my talk title. So I should at least tell you broadly what kind of materials we work with. And there's very, very many ways to rank these materials. You can rank them by band gap, you can rank them by melting point, bond length, atomic size, et cetera, et cetera. I like to rank them by dimensionality. So nanotube junctions, for example, I call these zero-dimensional objects. The junction itself is basically just a dot. Carbon nanotubes, of course, these are one-dimensional little molecules, basically. Then two-dimensional materials we work with are things like graphene, which is basically an unrolled carbon nanotube or a sheet of graphite. Boron nitride's another two-dimensional material, and molybdenum disulfide is another two-dimensional material that we work with. There's some others too, but these are the most common ones in my group. And then we work with what I call generally phase transition materials. Phase transition materials, these are three-dimensionally arranged bonding of these materials, but they have a switchable phase, and by that I mean they're switchable between an amorphous and a crystalline phase, either by the application of a voltage pulse, some sort of a thermal stimulus, or even a mechanical sort of bending type action, right? So these materials are very interesting for data storage and energy storage, and I'll talk about that briefly as well. Speaking of materials, it's interesting to kind of look at the abundance of materials on Earth. This, I believe, is actually on the Earth's crust, not necessarily in the Earth's core. But it turns out silicon is the second most common element in the Earth's crust. And so I sometimes joke with my students that if Intel could build CPUs out of oxygen, which is more common, they probably would. Except oxygen, of course, is not a good semiconductor at room temperature, as you know by breathing it right now. So, but silicon is a pretty decent semiconductor, so you can make chips and so on and circuits. But that kind of explains why silicon's pretty cheap, why we can afford to buy all these electronics, right? What sustains Moore's law? Silicon's cheap. Carbon, which is one element that we work with, is actually not too bad. Carbon is the 15th most common element on the Earth's crust. So, if you're going to launch technology on carbon, maybe that's not such a bad idea. Maybe it's economically possible. However, there are some other materials that we work with, and a lot of other people work with, such as copper, germanium, antimony, tellurium, lead, palladium, gold. Lead is down there somewhere too. These are rare materials, right? So if you're ever going to base, a technology entirely on antimony, I would say it's not going to take off. Probably, simply because there's just not enough antimony in the world. Unless, of course, you also have a friend who comes up with a really neat way of harvesting antimony from meteorites or wherever antimony happens to be available. I actually don't know if it's available on meteorites, but let's just assume that. And there's also geopolitical issues, of course, with some of these rare materials. There's tussling between big nations, obviously, about who owns what piece of material and for how much of the world's supply. So that could also affect the economics of these things. Anyway, back to science. So we work with graphene. Without much further ado, one of the first things that an electrical engineer does when he or she starts working with a new material is make transistors out of it, if you can. Graphene, it turns out you can make transistors out of it. So that's the first thing we did several years ago. And so obviously, particularly in my group, since we care about power dissipation in these transistors, we said, why don't we take these transistors and we do thermal imaging of them, infrared thermal imaging, very, very simple stuff. And we actually had some surprises in store. We made these transistors. There's the infrared thermal imager at the top. There's a gate at the bottom. And so this is kind of an upside down transistor if you're familiar with usually seeing the gate on top. But that's OK. It gives nice optical access from the top. And so we saw these beautiful, actually almost artistic looking hotspots dancing around from the source to the drain of the transistor and back, depending on what voltages we were applying. And so, of course, this sort of led us on an interesting runaround. This was, by the way, again, this is experimental data. And so then we started building the simulation model, trying to understand what was actually going on. At the same time, we could measure the current versus voltage curves for these transistors. Again, something very, very common that electrical engineers do. We measure IV curves all day long. And the first thing we noticed is that when the majority carriers in the transistor channel are, for example, electrons, the graphene transistor acts from a physics point of view pretty similar to a silicon transistor, an electron-type silicon transistor. So in this case, you basically have this blue line right here. You have a linear current regime, a saturating current regime, and basically that's about it. You get a hotspot that forms closer to one of the two terminals where you basically have a higher electric field and a lower carrier concentration. That's basically all that happens. But if you're a silicon transistor, if you're trained like me in the world of silicon transistors originally, this looks like nothing new. This is actually pretty uninteresting. The interesting thing happens, and the hotspot starts moving around when you're actually able to inject electrons and holes from the two terminals separately. And that's basically what's happening in the bottom right of the pictures right here. And this leads to the hotspot moving to the middle of the channel. I think I just lost my pointer. That's not good. Well, that's all right. You have a backup? Thank you. I can also just use both. Or OK, thank you. The interesting physics happens essentially when you have both electrons and holes essentially injected from the two contacts, and you get the hotspot in the middle of the channel. So you're actually learning some interesting things about how the heat is actually dissipated inside one of these graphene transistors. I should mention the resolution of this thermal imaging method right here is pretty coarse. This is a 10 micron spot, so the spatial resolution is something like 2 microns because it's limited by the wavelength of the infrared light that we're using. On the other hand, we've also done this with atomic force microscopes later on, and we actually confirmed that the physics is basically the same. So that's kind of nice that we were able to uncover this. I just want to get back to electrical engineering and away from physics for another moment and actually tell you that when you're in this operating regime with a hotspot in the middle of the channel, the current does this weird S-shaped thing at the top here. This is called an ambipolar operating regime. And the circuits guys and gals don't like it. This is where you don't want to operate a graphene amplifier. In fact, you want to keep it here in saturation. You don't want to keep it in the ambipolar regime. So probably you still want to operate in this regime right here, the unipolar regime. But it's nice to know sort of what the physics are for the other regime, which is not that useful for circuit applications. I mentioned modeling. We do some simulation modeling in my group. Sometimes simulation modeling is used to establish what kind of experiments we need to do. Sometimes we do the experiments first, like in this case, and then say, wait a minute, we don't understand these experiments, and we're going to come up with some modeling to actually try to explain them. So this is what happened in this case. We also have a habit of putting our simulators online. So if you go to this website called nanohub.org, you would basically get our simulator tool, GFET tool, and you'll be able to essentially run the same thing that my students were running in the lab or on their own laptops. You can actually run it in the nice graphical user interface inside your web browser. And if the rest of your talk is not that interesting, feel free to try this right now. Please let me know if it works, because we do want to maintain it for the community. So I mentioned a little bit about our work on transistors and actually mapping out the temperature distributions and the power dissipation and really the physics of operation in nanoscale graphene transistors, or certainly in small graphene transistors. What about data storage? It turns out when I was a graduate student, power use by data storage was not really a big deal. Fast forward a few years, And in 2010, Intel puts out this interesting paper showing that depending on the regime of operation, an Intel CPU is putting either about 20% or up to 70% into the memory of the CPU, right? This is just the memory part. This is not the logic. This is the memory. The reason for this is because as the memory has gotten smaller, it's gotten leakier. This is quantum mechanics, right? But the second reason is that we just have a lot more memory than we used to have, right? If you remember, 10 years ago, we were happy to have, I don't know, 256 megabytes of memory in our PCs, and now we're not happy with 8 gigabytes, right? So this has actually been going on, and all that memory is leaky and using power and not necessarily a good thing. So this has actually motivated us, as well as other groups, to go on a search for low-power memory devices. Again, in our case, from sort of the nanoscale, nanomaterial world. Long story short, we looked at the sort of what's out there. These are some of the memory. Don't worry about too much about the, these are sort of an alphabet soup of different memory types that are available out there. NAND memory, by the way, this is NAND flash. This is the memory flash, the flash memory that's available in all your cell phones right now, and some of our laptops as well. So NAND memory, is actually relatively slow, but it's reasonably energy efficient. In fact, what you notice, though, is that there's always a trade-off. There's no free lunch, right? There's always a trade-off between sort of, having a relatively low-power memory and having a sort of a fast but relatively energy efficient memory. So there's a trade-off between speed and energy, and that's a recurring theme in all of electronics, basically. And so we decided to look at one particular type of memory called phase change memory. The commercial type of memory is over here, but there are some ideas that we had about scaling it down to get basically down here somewhere. The question is, how do we get down there? Phase change memory sounds kind of fancy. It's not really in commercial products yet. It's more in sort of space-related applications. I think there's 1 or 2 cell phones you can buy here in Europe that have phase change materials replacing flash in them. So the manufacturers are testing the market. But I don't think you can buy phase change memory inside your cell phone in the US, at least. But certainly, it's almost commercial. It's a funny material. It's germanium, antimony, and tellurium. It's actually used in rewritable DVDs. This material or materials like it are used in rewritable DVDs. So if you own rewritable DVDs, you actually have this stuff already, even if you have Blu-rays and so on. On the back of a DVD, of course, the memory is written optically. It's written with a laser beam, and the laser beam basically just changes the refractive index of the material by essentially either crystallizing it or amorphizing it, depending on how much heat you put in with the laser. So that's kind of how it works optically. But it turns out that this particular material also has a large change in electrical resistance when you switch it between the 2 phases. And remember, you can do this reversibly, which is actually very neat for writing and rewriting memory. The problem had been, until recently, that very big industry players like Intel, IBM, and Samsung have been actually grappling with reducing the power per bit. Remember I mentioned power per bit earlier in transistors, where it turns out here was actually huge. For just 1 bit, the write currents were something like 0.1 milliamps, which if you multiply by volts, you're in the 0.1 milliwatts, essentially per bit, which is very, very large, actually. Of course, the read and write happens pretty quickly, but still, it's a pretty energy-consuming operation. Your battery would run out. So the idea that we had was, how do we scale this down? The indications were that as you make this smaller, it might get better, right? We just didn't, Samsung, IBM, Intel, and so on didn't necessarily know how to make it smaller, but the idea was sort of out there in the community. We certainly didn't come up with the idea that scaling it would make it better. We just sort of showed how to scale it, how to make it really small. So we took carbon nanotubes. Carbon nanotubes, I mentioned earlier, they're these one-dimensional, wonderful, wonderful electrical conductors. And their diameters are on the order of 1 or 2 nanometers. So it's absolutely impossible, to my knowledge, to make an electrical conductor that it's basically less than that functions reliably at room temperature, right? So we took individual carbon nanotubes and we used those as the contacts, as the electrodes, to probe phase change memory materials. And so without much further ado, I should tell you that we were able to contact bits of phase change material that are on the order of tens of nanometers, because the diameter of these things are so small already, right? And the switching power, the switching current, which is switching power basically, the voltages are the same, was about 100 times lower than anything the industry had shown up until that point. So even though we only built about 100 of these devices, that's still a very, very nice to know that it is possible, in effect, to actually build these things. We're not actually violating any kind of physical laws. It's actually possible to make these things probably even more energy efficient. So So actually right now, this is kind of on some recent and more recent and more ongoing work in my group. We're making what I call marshmallow devices. Actually, we've already made these and published these. These marshmallow devices, we really wanted something that's a little bit more thermally confined, because remember, this phase transition is thermally induced. So if you can actually confine the heat to a very, very small nanometer-sized volume, you're going to be able to bring down the power consumed significantly, right? So of course, no big surprise. This is what the marshmallow devices look like. This is of course just a cartoon. These were actually about a factor of 10 more energy efficient already than what I showed you on the previous slide. And right now we're making even smaller ones. We're making crossbar devices. So we're taking carbon nanotubes and we're putting them like this, like crossbars, and making the memory bit at the intersection of the two nanotubes. And that little intersection is probably an area of about 2 by 2 square nanometers, or 4 square nanometers, I guess, if you do the math, right? Which is about as small of a memory bit that you could probably make. Again, if you have a better idea, please contact me and we'll try to look into it. So what I'm excited about is that I think, again, our math shows that the theoretical possibilities that we can probably bring this down to attojoules, well below femtojoules to attojoules. And so there's, to paraphrase Richard Feynman, lots of room at the bottom, plenty of room at the bottom, right? To put this in context, this is what the data from industry was. This is actually a study summarized by Professor Philip Wong here at Stanford. And this is where our data is, both in terms of size and in terms of power. So we were actually able to bring down power and size at the same time, because they're actually related through these sort of thermal behavior of these bits. So we took something that is basically a nearly commercial technology, scaled it to somewhere here on this arrow, and now we're pushing it towards femtojoule, maybe less than femtojoule operating conditions. And the part that I'm excited about is that we haven't hit fundamental limits. I really think there's probably another factor of 10 to 100 to go until we really reach the fundamental limits of switching in this material. So that's really nice, because it's going to keep us busy for a while. All right. So I'm going to switch to the other side of the work that we do, and this has to do with how we deal with heat at the nanoscale. There's some really funny things that happen at the nanoscale, which actually can be scaled up to large dimensions as well. And I'm going to begin by mentioning just a bit about a fundamental understanding, some advances in fundamental understanding that we've recently gained, I would like to share with you. So just to give you the background on this, there's some peculiar things that happen in terms of energy transport at the nanoscale. For example, if you look at just the electrical resistance or the thermal resistance of a component, of a resistor, the resistance typically, as you learn in undergraduate or maybe high school classes, resistance scales as the length of a system. However, as you hit the nanoscale regime, the resistance becomes quantized, and the transport becomes what's known as ballistic transport, meaning that the electrons will travel from point A to point B without any scattering events. They'll just travel just like a ballistic missile, I suppose. Maybe that's where the term comes from. So whatever Ohm and Fourier taught us about electrical and thermal resistance, from back almost 200 years ago, no longer applies at the nanoscale. Again, just what I mean by the nanoscale is basically when the system size becomes comparable to the electron or phonon. Phonon is the carriers of heat, the vibrations of the lattice. Wavelengths or collision distances, these mean-free paths I mentioned, and these are distances on the order of tens of nanometers. And we're there today, basically, in terms of what we can make in our labs, as well as what people can make commercially almost. And what's actually interesting is that both the electrical and the thermal resistance are expected to behave this way. So has this been measured? Well, it turns out that electrically, it had been measured since about the 1980s. Van Wees, 1988, had measured this in quantum point contacts at low temperature. I believe this was gallium arsenide. So this has been done. Even in carbon nanotubes, electrically, this has been measured all the way up to room temperature by work done by Professor Hongji Dai here at Stanford back in 2004. Thermally, it was, to my knowledge, really only measured in a HERO experiment done near 0 Kelvin, not particularly useful for everyday applications. In fact, this was such a big deal that not only was it published in Nature in 2000, but they actually made a movie about it. The Uncertainty Principle, The Making of an American Scientist. It was actually about the measurement of the fundamental quantum of thermal conductance at 1 Kelvin, or maybe below 1. I think it was actually 300 millikelvins. You can look up the Nature paper. So that's really cool physics. But it's not happening near room temperature, so how does it affect me as an engineer who would like to have his electronics working at room temperature? So we had a hunch that graphene, one of the materials that we work with, which has extraordinarily high thermal conductivity, we had a hunch that these collision distances between phonons and electrons in graphene would actually be long enough to allow us to measure this effect at room temperature. So we built these test structures either as graphene, arrays of graphene nanoribbons, and this is the simulation of the structure. This is the actual experimental picture. And this is sort of the idea that we formed, both before and after our measurements. Basically, when we have long and narrow, actually, graphene ribbons, you have a lot of scattering, and you're essentially in what's called a diffusive transport regime. If you make really short graphene nanoribbons, it turns out even shorter than a quarter micron is fine. You're in what's called a quasi-ballistic, or you're approaching this ballistic quantized conductance regime that had been theoretically predicted but never measured at room temperature. And so, again, to make a long story short, we measured this, ranging from room temperature all the way to lower temperatures as well, but not too low. I mean, from about 170 to 100 Kelvin, all the way up to room temperature 300 Kelvin. And to our surprise, we found out that we can actually, not only are we approaching these so-called ballistic limits at room temperature in this material, so energy, heat flow, is actually approaching the ballistic limits at room temperature in this material in samples that are small enough. Not only did we find that, but we also found out that we can actually manipulate the way that heat flows in these nanoscale devices by changing the dimensions of the device, right? So normally you think of something like thermal conductivity or electrical resistivity as a immutable material property. It turns out as you shrink the device down to these dimensions, the thermal conductivity becomes a function of the device length and a function of device width. So you can't use the bulk parameters that you would look up in tables or in other papers that people have written about this material. And by the way, the same would probably apply in silicon, just at probably lower temperatures and smaller dimensions. But it just happens that in graphene, this actually occurs effectively at room temperature. So that's very interesting. As I promised you, that is relatively fundamental study. On the other hand, people are talking about making interconnects out of graphene, right? People are talking about replacing copper for interconnects out of graphene. So of course, those will be introduced at technology nodes, which are very comparable to the dimensions that we measured in our lab. So if you're going to make interconnects out of graphene, you probably really should be realizing how the thermal conductivity of these ribbons will actually change as you change the dimensions of the device. So a little bit more about managing heat and maybe even harvesting heat from a more practical point of view. There's a lot of heat in the world, right? This is sort of an obvious statement. Almost everything that we do wastes heat. Certainly power generation plants waste heat, transportation wastes heat, engines, friction, et cetera, right? And as we found earlier, computing wastes heat. You can cook breakfast on your computers. And it turns out there's so much of heat wasted in the world that the Department of Energy estimated that there's about 15 terawatts of heat wasted in the world, right? Just kind of warming up the atmosphere or warming up our breakfast. So it also turns out that most of this heat that is just lost in the world from all kinds of industrial processes that we undergo is relatively low-grade, what's called low-grade heat. Low-grade heat means the source of the temperature is pretty low, something like below 200 Celsius. That number is probably arbitrarily set, but let's call that low-grade heat. So recovering even a fraction of a % of all this wasted heat would be huge, probably the equivalent of power plants, which are gigawatts, right? So we're talking about actually very, very large numbers. In fact, this is a cartoon of a power plant, but even just looking at cars, something that I have a little bit more intuition about than power plants, if you look at this cartoon, from the 100% energy that comes in through a gallon of gas, only about 12.6% is actually used for moving the car down the road, right? So the rest is lost in friction, it's lost and lost as heat, obviously, right? And some of it is obviously lost in powering the electronics in the car. So the solution, a possible solution to this, other than making things more efficient to begin with, is to deal with the heat that you're generating anyway and to just recover some of it using these materials called thermoelectrics, right? Now, thermoelectrics have been around for over 100 years. They've been around for over 100 years. In fact, the Russians, I believe, during the Second World War, maybe right after it, they were selling a thermoelectrically powered radio where you could stick one end of the radio, I guess, into your campfire and the other end into the frozen tundra and sort of listen to Stalin's speeches. So the Russians have already done it. What's preventing us from doing it? Well, I'll get to that in a moment, but just a little bit on how thermoelectrics work. Basically, there's two modes of operation for thermoelectrics. One is first using basically an electrical current to heat or cool something. So this is what's called the Peltier effect, right? And you can actually develop either a heating or a cooling power by running an electrical current through a sequence of little thermoelectric legs that look like that. And the current will be, the heating or the cooling power will be proportional to the current you're running, the difference of Seebeck coefficients at a junction. Seebeck coefficient is basically the property of the material. And then the temperature which the junction operates at, right? And by the way, this is used today in small refrigerators. So if you go to Sam's Club or Bed Bath & Beyond, I think you can purchase a small wine fridge that is quiet, has no moving parts, no freon, and is powered by thermoelectrics, right? If you have a really fancy car, I am told, you can also buy a car with thermoelectrically cooled car seats. I think these start on the BMW 8 Series. And it's an option. So you don't get it with the base price. That's what I'm told. And of course, if you also get some of these fancier cars, you also have a thermoelectrically cooled cup holder, right? So you can put your whatever you're drinking while driving, right? So anyway, these things exist. I mean, these are real things, and they have no moving parts. They're quiet. They're reliable. There's no freon. They're clean. So why don't we use them more commonly? Before I answer that question, let me just tell you about the opposite mode of operation. In the opposite mode of operation, we would use a temperature gradient, such as that between the car engine and the air, right, to generate power. So this is what's called the Seebeck effect. And in this case, you basically generate a voltage by having a temperature gradient and having some Seebeck coefficient across it, right? And this too is being used. It's actually used in car engines, again, BMW. This is a picture I took from a BMW article. BMW is supposedly recovering something like 600 watts from their exhaust system just by covering it with thermoelectrics. 600 watts, that's about 1 horsepower. So it's not going to make a huge difference in your gas mileage, but it's kind of cool to talk about. So maybe at this point it's more PR than gas mileage, but it's there. It can definitely power your electronics, therefore leading to a smaller alternator in your car. And what I think is really cool is that the recently launched Mars rover, the Curiosity, that's currently roaming on Mars, is powered by thermoelectrics too. It's not powered by solar panels, right? The previous generation was powered by solar panels, but solar panels failed. They got covered with dust. Maybe Martians, played with them, damaged them. But the way the Mars rover works is it actually has the little rover, right? It's the size of a car itself. It has a plutonium heat generator inside. Right, and the plutonium heat generator is basically it's a long-term heat source. It's in there. It's generating heat. So that's the hot end of the thermoelectric, and then the cold end of the thermoelectric is probably the outside chassis of the of the little rover, right, which is the cold Martian atmosphere, whatever there is of it, right, and that generates about 100 watts as well in terms of power, and that's enough for this thing to roam the planet and send back pretty pictures. Now, and again, you can probably kind of piece these things together and sort of realize maybe why these things are not more prevalent in our lives. They seem to show up in really high-end, expensive applications, right? The physics is there, or it's almost there. It's fairly well understood in bulk materials, but clearly cost is an issue, right? So, and actually, speaking of cost, here's some of the materials being used. Traditional thermoelectrics are based on bismuth, tellurium, lead. These are basically toxic, rare materials. They're probably way at the bottom of what I showed earlier in terms of where the materials are on Earth. They're certainly toxic. They're brittle if you want to make flexible things out of them. And look at the cost, right? Expensive and rare go hand in hand. So the cost for these is hundreds of dollars per kilogram. And then we have other materials that apparently have some properties similar to thermoelectrics that cost a lot less, right? So one of the ideas that we came up with, and this is something we're investigating currently with Professor Jianan Bao in chemical engineering here at Stanford, is to start with a special kind of polymers which already have 2 out of the 3 properties that you need for thermoelectrics. And those are low thermal conductivity and reasonably high electrical conductivity. It doesn't have to be as good as a metal, just relatively high. So you obviously need conducting polymers, not the insulating kind. So you need high electrical conductivity, you need low thermal conductivity. And then you still need something called the Seebeck coefficient. You notice that that keeps showing up. And so then use nanostructuring, meaning some form of nanoscale manipulation of these polymers, to increase the Seebeck coefficient of these materials. This has actually been thought of by putting, for example, I think people have talked about putting nanoparticles in even conventional thermoelectrics to increase their figures of merit. So there's some active work in that. There's been much less work on the low-cost polymers, right? So if you can start with something that's already very low cost, and maybe make it a little bit more expensive by tweaking it a little bit, but not as expensive as these naturally occurring materials, maybe you have something on your hands, right? So that's actually an ongoing project in my lab right now that we're really, really excited about, and we're really trying to actually make low-cost thermoelectrics based on relatively abundant polymers, which already have 2 out of the 3 properties needed for these kinds of applications, right? As a bonus, because we're working with thermoelectrics, these are actually, this is my student's hand, and obviously working with a pretty small sample, but small enough that she can actually bend it. And so this is actually a bendy little piece of polymer. So that's an advantage. These things are brittle. These polymer-based thermoelectrics are actually mechanically flexible, so you can imagine putting them like maybe in your clothes or something like that, or on bendy surfaces. And they're also solution processable, which should lead to or should keep the cost down, I should say. Anyway, I'm going to wrap up by essentially kind of going back to the beginning. So I mentioned these factors of 10,000 in terms of lowering sort of the needs to lower power by about a factor of 10,000. So please don't take this slide too seriously. It's just meant as food for thought. But if you are able to reduce all the power of all the data centers in the US today by a factor of 10,000, you'd be down to the power of 1 megawatt, and that's the power of 2 Ferraris. If you want to know where you can get that power from, it's roughly the solar power you can harvest from 1 parking lot or something like that. These are still pretty big numbers. You could say, well, I don't own a Ferrari. That sounds really strange. I see them all the time on El Camino, but I'm just not used to them. I certainly don't, like I said, big numbers. It's really, I really, sometimes it's hard to put them in context. So, okay, so let's look at something a little bit closer to home. I think most of us own something like this. A smartphone uses something like 50 milliwatts, time average. Obviously, it uses up more when you're doing things like making a call or downloading video. But on average, over 24 hours, if you don't do anything too unusual, it's probably using something like 50 milliwatts. You scale that by a factor of 10,000, and you're down to 5 microwatts. And 5 microwatts is the power used by a wristwatch, right? I have one of these. Actually, mine is, I'm sad to say, it's battery operated. But I did buy my dad one of these watches for his birthday that's solar operated, right? And not only that, but there's companies that actually make watches at 5 microwatts, right, roughly, which are powered not only by the sun, but powered by your wrist movements, powered by also the heat that your wrist is putting out. Right? So it's clearly that even with today's technology, you can recover 5 microwatts of heat from your wrist and power a little watch. Right? So that led me to sort of ask myself, well, what is the maximum amount of power you can recover from a human body? If you were to cover yourself head to toe in thermoelectrics today. It's a funny mental picture, but just for a moment, what are the limits? Well, the limits are set by the Carnot efficiency limits. So if you're familiar with those, you'll know that it's sort of T hot minus T cold divided by T hot. And what's T hot, what's T cold? T hot is the skin temperature, let's say, right? 35 Celsius. T cold is whatever the air temperature is around us. So if you're in Singapore, it's also 35 Celsius. But if you live in more temperate climates, it's probably like 20 Celsius or something like that in this room. So you have something like a 15-degree temperature difference that you can do something with, right? You wouldn't be able to, by the way, recover too much thermoelectric body heat conversion in Singapore if it really is 35 Celsius outside. But here you might have a chance. So anyway, long story short, kind of going through the numbers, I realized that you can probably recover something like 1 watt from the human body today if you're covered with thermoelectrics. Which means I cannot power my laptop using my body, right? Unless I go running, which I'm going to generate much more than 1 watt, but that's not a very fun way to power your laptop, is to go for a run. Well, some of you might think it's fun. So I prefer to generate my heat sitting down, I suppose. And of course, but that's kind of nice to know, because 1 watt is a heck of a lot more than even what my smartphone uses today, right? And people talk about, a lot of my colleagues talk about, covering ourselves with sensors. Healthcare talks about covering ourselves with sensors. People talk about these body area networks. The power's there. You're the source of power, actually. So it's doable without breaking Carnot's limits, right? By the way, you can also recover energy from walking, obviously. But this sort of, again, runs against my own philosophy of not having to do too much work to power my electronics, right? And even then, I think people have estimated something like 4 watts from walking if you have sort of these piezoelectrics in your shoe heels. So even that's not quite enough to power your laptop. It's still something like powering your smartphones, your sensors, and so on. OK, my last slide, I promise. Second to last slide, actually. So anyway, just to summarize, I really think from the point of view of an electrical engineer, and of course you can tell a lot of these things are sort of tainted by my view of being steeped in Moore's law, so to speak. Moore's law maybe will get us another factor of 10 in terms of improvements, right? Maybe a factor of 5, and then we'll stop. But it's really slowing down. On the other hand, I really think that thinking about electronics and thinking about what to do with electronics and with the heat all around us, I think there's opportunities for factors of 10,000. Maybe we'll meet somewhere in the middle, but certainly we can do better than factors of 10. And I really think this is the part that I'm excited about because obviously I work in this field. I'm really looking and I'm excited about a convergence of ideas in low power electronics. So that's one of these areas. Energy harvesting, which I also described. So basically just getting whatever energy you can from the environment. And then novel materials, ditching silicon, right, for things that silicon is not necessarily the best material at. And I really think it's actually kind of neat to think about really what the fundamental limits are. Because those are ultimately the limits that are going to tell us whether something's going to work or not at the end of the day. So we do a lot of that as well. We try to think about, are we violating some fundamental law when we design this device? I should really thank the people who are doing the work and the people who are paying for it. So it's a picture of my graduate students and some of my alumni. We're still a relatively new group. As I mentioned at the beginning, we had been at the University of Illinois for 6 years. So we've only graduated 3 PhD students, but we have a few more in the pipeline. If any of you are from industry looking to hire these students, obviously get in touch with me. And of course, our collaborators. A lot of these things are simply not possible without our amazing collaborators. And across many, many institutions and many, many departments, because what we do is really, I don't even know, I certainly wouldn't be able to do it on my own. Thank you.
Okay, well, thanks. That was great. We have some time for questions, and we like to try to start with the students first. Okay.
So in your phase change material, you were talking about how you could really decrease the amount of energy consumed. And I was wondering, is that due in part to the ballistic transport through the nanotube? Or is it because you're confining the actual phase change material? Or is it something else?
No, actually, that's a very good question. So it is, the ballistic transport in the nanotube helps, but it's not the main player. The main player in this case is basically thermally confining and engineering that little bit, right? The nanotube, to be honest with you, is great because it enables us to contact really small volumes of material, much, much smaller than you could contact with a piece of metal, right? With a patterned piece of metal. But the nanotube is sort of like, just delivers the voltage pulse and gets out of the way. Right, it adds like a very, very small amount of series resistance if we make some mistakes doing processing, but otherwise I think the nanotube accounts for up to maybe about 10% of the total resistance of the bit, and the rest is really delivered at the location of that little nanobit. So in other words, the nanotube does not have to be ballistic for this to work. The nanotube can be even kind of a bad nanotube will actually make this work pretty well.
Okay.
So if you guys can find a way to make the whole thermoelectric process a lot more cost effective, do you see it being possibly used on commercial scales or more of a macro scale? And you're like building energy efficiency rather than just.
That's what I would like to think. Yes. Yeah. I mean, I think if you look at the cost of the starting materials, I think that's a very encouraging thing, right? So I think a lot of people who have worked in this thermoelectrics business, they've sort of started with some of the similar materials and tried to improve their efficiency by nanostructuring those expensive materials. So now you're starting with an expensive material and doing some other really crazy processing to it, and it's only going to increase the cost, right? So you might make it more efficient, but you're also going to make it more expensive, right? So on some level, I think that it might be okay to take a hit in efficiency if the cost is a factor of 1,000 times lower, right?
And to kind of further the question, do you think that the resources are available to make that a commercial item?
I mean, we're looking,
Physical resources, not money or anything like that.
are there factories in place to crank out these polymers and the nanotubes or whatever you want to put in them? Is that what you're asking?
No, the materials themselves.
Yes, sure. The materials are here. Yes, yeah. No, the materials are here. Yes, and actually that's where the expertise of our collaborator in chemical engineering, Professor Jinan Bao, comes in. But yes, these are very, very common conductive polymers.
Do you have an idea of how much you have to reduce the cost by in order to make something like a typical refrigerator run by those electric things?
Now you're asking me an economics question. To be honest with you, I don't know, actually. I'm not exactly sure how much. Are you talking about the bismuth tellurides or even the polymers?
So the refrigerator that's powered by those thermocouple things,
yes,
presumably uses bismuth telluride. You're right.
Yes, that uses bismuth telluride.
But that's a high-end product. It's expensive. How much do we have to reduce the cost by in order to make that work on my refrigerator?
I think you'd have to go to Sam's Club and look at the thing, what it costs, and look at the scale of it, right? I think these are like 5 cubic foot fridges. They cost like a few $100s, right? So it would probably put the cost of a 20 cubic foot fridge, right, that you probably want to have at home, and I'm just making a guess, into the several thousands of dollars. So I'm sure, if you wanted to, maybe somebody's making one of those, like a $5,000, $10,000 fridge for your kitchen, right? But so maybe I just answered the question that you said. Maybe for large fridges, maybe it's a factor of 10. Maybe on the order of that, but really, I could look up the answer for you actually, but you could probably look it up yourself too afterwards. Yeah.
All right, one back there, and then there, and then we're going to wrap up. Yeah.
Great. So you're talking about reducing power by, you've done 100 times lower. Are you sacrificing speed of switching by doing that? Or
Surprisingly, no. No, actually, the speed was nanosecond speed. Yeah, so it's good enough to be replacing DRAM actually. Yeah. Yeah, so that's actually something that, it's there. It works. It's not breaking physical laws. It's just by slightly better thermal engineering and judicious use of materials, right? Is this going to be showing up in commercial products anytime soon? I have no idea. We've built a few hundred of these devices, right? Can we make billions? I certainly can. Not with my students and my $10,000 in research funding, right? But if Samsung or IBM or Intel wants to throw $1 billion at it, $100 million at it, and 1,000 PhDs, it might happen, right? Oops, sorry.
Okay. And anyway, Roland. Yep.
How about manufacturability? How do you lay down 1 billion nano cup?
Yeah, that's the $1 billion question too, right? So it turns out, I don't know if I have a picture of this. Actually, we have lots of, a lot of my colleagues are struggling with this exact question, more for transistor and solar cell work than for memory. But it turns out that it is possible to grow almost perfectly aligned carbon nanotubes today. So if you look at this picture right here, this is a cartoon, obviously, but this is a real picture, and this is a scanning electron microscope of 2 carbon nanotubes, which we were able to put perfectly at 90-degree angles, right? And this was actually done by hand by a graduate student. And what you can't really see in that picture is that there was actually a lot more nanotubes in there, but he etched them away, right? And so it's possible to do this today. Obviously there are some challenges. The challenges are we can't really get the density high enough. So we have some ongoing projects in electrical engineering where we're working with Professor Philip Wong to try to increase the density of these nanotube arrays. But you can actually get them nice and parallel. That's actually kind of neat, right? And so the idea is if you just grow the parallel arrays and then you take a rubber, it's almost like a rubber stamp, and you just peel them off, you can stick them onto a different substrate, and you just repeat this process until you get several hundred of them per micron in terms of alignment. And you just need to be a little bit careful, but it has been done. I think the world record is something like 100 nanotubes per micron width, and that looks already pretty darn dense. That's 1 nanotube every 10 nanometers on average, which is dense.
Okay. All right. Well, I think we're going to wrap up. So please
Thank you.
welcome Eric to the community, and thanks for the great talk.